Okay. Hi, AP Physics. This is really weird, and I miss you so much. And right now, my students, I should show you. Olivia has them set up, but then I just kicked them. Are these girls instead of you? Not as fun. So welcome to my basement. There's the play area. Sometimes you'll probably hear kids. I'm going to try and do this when they're sleeping. And I set up a board, and we're going to try doing some kind of mini lectures from my basement. I grabbed everything I could when I left my classroom, so I've got some demos as we get into later things. So your first lecture is a review of Coulomb's law, which you have seen before. I don't know if you remember it. So we're going to run through. I'm kind of following along the PowerPoint. It's not going to be the same exactly. But what I want to get through in this first little short video are some of the properties of charge. So with part of that, we'll talk about terminology. Specifically, I really want you to know about atom and how charge works in an atom and what induction of charge is. And then we're going to review Coulomb's law and talk about like what the shell theorems conceptually mean for Coulomb's law. I will do a separate video for you to watch with some practice with Coulomb's law, and so I'll do some problems with that later. Okay, so charge. It's really hard to talk about it without talking about the atom. So we'll start there. Historically, all of this stuff, electricity, magnetism, does not get studied in earnest until after the 1800s. So people had observed a lot about what we now call electricity before that, but the mathematical support came along later in physics. So people first noticed electrostatics, which is what we're studying. And even before they had the thorough understanding of the atom and its structure, they noticed things that you probably are noticing at home. If you're bored, you can try any of these things. If you shuffle along the carpet, especially if you're in like thick socks and then you touch something metal, you'll feel that zap. And so that's because of some buildup of something, right? We call it electricity. Sometimes you might notice with like if you have thick blankets in the dark that there will be sparks when you move them. You know, the balloon on your hair thing, we did that last year. So all those things were observations about charge. And so that was noticed many hundreds of years ago, in fact. And once there was a good understanding of the atom and its structure, it became clear that that was the origin of charge. So as you know, the atom is made out of a nucleus that's really tightly bound, and the nucleus has protons and neutrons, so it would have a positive charge. And then you've got this electron cloud around the atom, and that is where we have the negatively charged particles. So when we are charging things, it is generally through a manipulation of that electron cloud, because to get to the nucleus and break it apart and pull a proton involves nuclear, usually fission, and that's not something that we would do. So all charge originates in the atom, and when we are manipulating charge, we do it by messing with electrons. So to charge something, we either add electrons to something or take them away. Obviously, if we add the electrons, then the object overall is going to have a negative charge because it has more electrons. And if we take away electrons, the object overall would have a positive charge because the nucleus would have more protons than there are electrons. So the easiest way to do that in electrostatics is, you know, again, the balloon is a great example. Sometime I'll make Hannah do this for me because her hair will go crazy. But if I took a balloon and I rubbed it on my head, both the balloon and my hair would be neutral before I did anything. And then in that physical interaction, maybe my hair starts to lose some electrons and they stick to the balloon. So the balloon would become negative, my hair would become positive, right? So that's how charge kind of originates in the atom, and then we would take these electrons and we want to get them to flow somehow. And so when we get charge moving, that's what we call current, but again, that's in our future, like, I don't know how many more videos from now, but sometime we'll talk about that. But it's a manipulation of electrons that gives us charge. Now, if we manipulate the electrons and charge something, we can do something called induction. And so induction, I showed you last year, and again, maybe I'll get Hannah down here later. Induction of charge happens when you take, like when you took the balloon and you stuck it to the wall. So if this is the wall, which has a currently neutral charge, so this is the wall over here on the right side. So neutral, plus, minus, plus, minus, plus, minus, plus, minus. Now it's clearly not that simple. This would all be atoms, etc. But the point is it's neutral. The same amount of positive charge as negative charge exists. When I touch this dry erase in my basement layer, I am not zapped. And let's say I take a balloon up to the wall. Oh, my furnace turned off, it got loud. I take a balloon up to the wall, and the balloon I've rubbed on my head. And so I've given the balloon, let's say, an overall negative charge. I don't know if you can see this. I should move the camera. Do you see overall negative charge? So if I take the balloon and push it towards the wall, there's an interaction, an induction of charge that occurs. Induction of charge happens because positive and negative charges repel each other. No, they don't. Erase this video. Positive and negative charges attract each other. Sorry. Negative, negative, positive, positive will repel each other. So we would say like charges repel, opposite charges attract. I think you all know that. So if I take the negatively charged balloon up to a neutral surface, what happens is the atoms and the molecules in this surface will shift such that the positive ends are closest to the balloon and the negative ends are going to be pushed away because of repulsion. So the wall overall still has a neutral charge, but there's a shift in how that charge is distributed so that there would be a clump of maybe more positive charge right here. The balloon could come to the wall and it could stick. So that action is induction of charge, also described well in your textbook, which you are going to start to use from now on. Let's get into, I guess, Coulomb's law. So all of these things about electricity are pretty easy to observe. Just, you know, like I showed you some of these things last year. I don't know if you remember, we had like, do you remember we had dead rabbit's fur? We had like rubbed the plastic and held it over little pieces of paper and things like that and saw it move. So all those things you can observe just through simple experimentation. So people had for years. So Coulomb came along and tried to actually quantify what he was seeing. And so, I'm going to erase this, sorry. Okay. So he realized that, as I already said incorrectly at first, opposite charges attract, like charges repel. There has to be some kind of a force that is happening there. And it is what we call the electric force. The electric force is one of the field forces, so it can act at a distance. These things do not have to be touching each other for the force to exist. So Coulomb was trying to quantify the electric force, so he figured that the electric force had to be related to two different things. One, the charge itself. So if you have a really small amount of charge, you're going to have a smaller force than if you would have a large amount of charge. That makes sense. And the other thing is distance. So if in the balloon example, if I rubbed a balloon and it was on the other side of my basement, my hair is going to stay exactly the same. As I bring it closer to my hair, then you might see some kind of change, right? So distance and charge were in some way related to force. So he thought that force and charge, we use Q for charge. So we would say Q1 and Q2 because it's going to always be between two or more charged particles. So force and charge are directly related. And he said force and distance must have been inversely related. We use that R for distance still. Now, when he actually did the experimentation, it turned out that it was inversely related with this. It was actually to the square of the distance. So he did a lot of experimentation measuring electric charges. I'm moving this so you can see the other side of the board. Sorry about that glare. He did a lot of experimentation looking at, okay, like what can I do to put an equal sign in there? You can read about the experiment in the textbook. Since I'm trying to make these videos short, I won't get into it now. But it was a pretty simple experiment, very clever. And he ended up finding that electric force, now we see this written two ways. Last year you saw it this way, is equal to Q or K times Q1 times Q2 over R squared, where K is a constant. It's called the permittivity constant. It's equal to 8.998. So I would say 9 times 10 to the 9th. Newtons times meters squared per charge is measured in coulombs, so per coulomb squared. Or you can say this is equal to 1 over 4 pi epsilon naught times Q1 times Q2 over R squared. Now in AP you see this 1 over 4 pi epsilon naught more because epsilon naught is a given, I know again you can't see that really well, is a given that we use later on with other electrical things. The point is K is equal to 1 over 4 pi epsilon, epsilon being a Greek letter. They're the exact same thing, okay? They're both a constant that came out of experimentation. It's a really big number, actually. So if you're looking at this equation, I would like to think that it looks familiar from back in our pre-this craziness days a couple weeks ago when we were studying gravitation. So gravity was the first field force that was quantified by Newton. And he said it's equal to big G, some constant, times M1 times M2 over R squared. So this field force, electricity, is equal to K, or this other one, some constant, times Q1 times Q2 over R squared. So it behaves very much like gravity, like almost exactly the same way. Two big differences. One, it can be attractive or repulsive. So the force can be, you can push charges apart or it can pull them together. Gravity is only attractive. And the second thing is this force acts at much smaller distances. So it's obviously got a very, very different constant, and it is a short range force. Gravity is acting like across huge distances in space. This is acting across very small ranges. So that's electric force in a nutshell. To do the problems, which will be a different video, aren't tough, but it's going to look a lot like gravity. It's a force, so it's a vector, so you have to start with a free body diagram when you do it. The last thing on the agenda for this little video was this, if we go back over to my other, oh, I'm turning the computer instead, sorry guys, I'm adjusting, was the shell theorem. Now, I had mentioned to you that we are going to see a lot of shell theorems in E&M. This shell theorem is just conceptual for now, and then we'll really dive into it. I don't know when, we'll get to it sometime, April maybe. So the shell theorem says two things, and both of these things are on your PowerPoint, so I'm following along the PowerPoint if you're with me. It says that if a charge is outside of another charge, which is typical, right? So I have a positive charge here and a negative charge here. And let's say this is something that's, you know, a balloon, or it's not necessarily an atom, like a charged object, and here's another charged object. The force between these two things acts as though all this positive charge is at its center and all this negative charge is at its center. Kind of like, remember gravity, like we treat it as though all the mass is sitting right at the center, even though it's distributed all over, let's say, Earth. So we do the same thing here. Does that change how we treat it mathematically? Absolutely not. It's just a conceptual thing for right now. Where this gets interesting, it's just like the shell theorem for gravity. If you go inside a charged particle, and there's proof for this, and I'm not proving it right now on this short video with this little board, so let's believe me right now. If you go inside a charged object, so go into the shell, this is a shell theorem. If you go inside the charged object, then the net force, electric force acting on the charge inside is 0. And that becomes very important. So it might not make sense yet because it's really totally abstract, but that is the second part of the shell theorem. And when we get into Gauss in our future, I'll keep bringing it up. So for now, I will stop because that is all I have to say about the behavior of charge. Bye, girls.